Welcome back to ECE 501B. Contrary to what was mentioned before we came on air, these assignments are not all due today. They're due at 3 different points in the near horizon so that we can be ready for exam number 2, which is on the 2nd of November. And that's coming up pretty fast. That's 2 weeks from today, I believe, in terms of exam number 2. And today is not the due date for homework number 4. It's tomorrow, just to be a little bit different. And then the next homework assignment 5 is due a week from tomorrow. And then the 31st is the Monday before the exam on Wednesday. Today I've actually given our time together a title, calling it the Orthogonalization Lecture, just because I like to say that word. No, I probably am going to stumble over that word, but we're doing a lot with this concept of orthogonalization in today's class, and I want you to appreciate what that is and the power that it actually provides to us. We'll start with a little recap of where we ended up last time talking about orthonormal lists, and that was the norm of an orthonormal linear combination. We really just take the scalars of those vector descriptions. We've described a vector as a linear combination of orthonormal vectors. Their scaling is then we take the absolute value of that, square it. That's the norm of the orthonormal linear combination. Today we will start with looking or showing that if we have an orthonormal list, it's linearly independent. Then we will present the orthonormal expansion of vectors, another very powerful idea. We'll learn how to create a set or a list of orthonormal vectors. If we start with a set of linearly independent vectors, and that's the Gram-Schmidt orthogonalization. We'll then present a few corollaries, 4 of those. Then at some point we will start talking about orthogonal projections, and that's going to be the orthogonal complement. If we have a subspace or a subset, what's the complement to that subspace or subset in the overall vector space? That's this orthogonal complement, and we can then start creating a direct sum decomposition by summing up these different vectors. And I don't know that we will get there today, but we can then start talking about a projection operator, and this will allow us now to get into optimization type problems. Maybe we want to find a solution in some subspace or in a subset. How do we now maybe get to or find the shortest vector in this subspace that's nearest a vector that's not necessarily all in that subspace? And the orthogonal or the projection operator will allow us to do that. This is what we ended with, I believe, last time, was proposition 25 in chapter 6, and it's under the subheading of orthonormal lists. Here, this is talking about the norm of an orthonormal linear combination. There's a lot embedded in that description. We have a linear combination. You know what that is. That's scaled versions of vectors. The vectors, though, are specialized. They're orthonormal, which means that they are orthogonal to each other, and they have a length of 1 or a norm of 1. I shouldn't say length, but they have a norm of 1. And now we want to know, if you give me a vector that's made up of a linear combination of orthonormal vectors, how do I find that norm? And this proposition states that. We'll start with this list, this orthonormal list, which means they're pairwise orthogonal and they have unit length, each of these vectors. And if we create a vector v as a linear combination of those vectors from the orthonormal list, then that's we're using the property that those vectors have a norm of 1 to just write down. All we really have to do to find the norm squared is to take the absolute value of each of these scalars and square it and add those up. And that's all playing on the fact that E1 is orthogonal to E2. E1 inner product with E1 gives you the norm squared of E1, but the norm is 1. These have been normalized, these vectors, and so the scalar's absolute value falls out to provide this fairly neat meaning not wow, but clean way of finding the norm squared of a given vector. Then we can talk about the next corollary, which is dealing with an orthonormal list, and that list, if it's orthonormal, is actually linearly independent. That's the title that the book has given this particular corollary, and really the corollary itself doesn't say much more than what the title says. But here, every orthonormal list of vectors. So if you give me an orthonormal list, then those vectors are linearly independent. So every orthonormal list of vectors is linearly independent. And the proof of that can actually be presented fairly nicely based on the previous result. So let's now take a list of vectors E1, E2, E sub n, and we're assuming that that is an orthonormal list. And that's what's given as a part of this corollary. We're given an orthonormal list of vectors. So let's just take that. And now suppose that we find coefficients A1 and scale E1, A2 and scale E2. Suppose that we can find these scalars such that when we add up those scaled vectors, A1, E1 plus A2, E2, we can find those scalars to give us C. But if we can write that, we can now use the previous proposition or theorem, proposition 25 of chapter 6, what happens if we now wanted to look at that? That's just a vector. This is now a vector, essentially. What do we know about the square of the norm of that vector, or what does it look like? So now we have it's equal to 0, obviously, if the linear combination is 0. But now if we look at the norm of that vector, squared, based on proposition 25, how do we compute that, or how can we express the norm squared in terms of these vectors and scalars? So now we just take the scalars, take their absolute value because they can be complex, and square those and add all of those up. But now we're saying that that is actually equal to 0. But if a sum of non-negative values are 0, what does that say about any or all of those non-negative values or numbers? They all have to equal 0, or we would not be equaling 0. So that particular norm of a linear combination of orthonormal vectors allows us to say that, oh, once we write the norm in this way, we can now see that every one of those coefficients actually are equal to 0. But now if we realize that if we write this equation now at the top of the screen, and we find coefficients a1 through am that force it to 0, and the only coefficients that cause that to happen are when the coefficients are 0, what does that tell us about those vectors? They are linearly independent, and that's our proof. And that fell out immediately from the norm of a linear combination of orthonormal vectors. Well, now if we have these orthonormal vectors, maybe we can create basis vectors with those, because we should be able to extend those. We know we can do that to fill our vector space, or orthonormal basis is an orthonormal list in our vector space V that is also a basis on. If we have a basis on our vector space, what properties do those vectors have to possess, or what properties do they satisfy or give us? We have a basis. They span V and they're linearly independent. So this now spans the vector space and they're linearly independent. So an orthonormal basis is an orthonormal list. We just showed that an orthonormal list is linearly independent. And if it's a basis, then it spans V. So we're given these two. If somebody gives us an orthonormal basis, then we have an orthonormal list that does both of these. It's linearly independent and it spans V. Any orthonormal list orthonormal list in our vector space V that has the number of vectors in it, the length of the dimension of V, is in fact an orthonormal basis. So if you build up this orthonormal list and it actually has the number of vectors in it equal to the dimension of our vector space, then that forms an orthonormal basis. For our previous result, corollary 26, chapter 6, showed that the list was linearly independent. And a linearly independent list and of the correct length correct length is the length of the dimension of our vector space, actually does provide us with a basis. And these are actually quite handy. Orthonormal bases. We could have many different orthonormal bases for a given vector space. Orthonormal bases are handy. Because it's easy to use those to actually decompose vectors. Which leads us to the next theorem, Theorem 30, which is titled Writing a Vector as a Linear Combination. Of an orthonormal basis. In this theorem, if we have a list, E1, E2, E sub n, and that n is now the same as the dimension of our vector space, we now have n of those orthonormal vectors. If E1, E2 through E sub n is an orthonormal basis, on our vector space V, and we take a vector V that's in that vector space, then we can rewrite V as V inner product with E1, scaling E1, plus the vector V inner product with E2, scaling E2, etc. down to V inner product with E sub n, scaling E sub n. That's a way we can decompose, or we can express any generic vector V in our vector space, capital V, as a linear combination of this orthonormal basis, E1 through E sub n. And what do we know about the norm squared of that vector? What are these individual inner products? Inner product of V, E1. That's taking two vectors, the vector V and one of the basis vectors, E sub L, and forming the inner product. But an inner product does what? Takes two vectors and produces a scalar. Each of those bracketed pieces are scalars. So those are A1, A2, A3 that scale these orthonormal vectors, E1 through E sub n. If that's the case, what happens, or can we now think back about what we just talked about in terms of how would we write the norm of that vector squared? So it's now the absolute value of A1 squared plus the absolute value of A sub 2 squared, but here let's go ahead and keep the parameterized form of A1 is simply the inner product of V with E1. We take its magnitude and square it. Then we take the inner product of V with E sub 2's magnitude and square that, etc., until we get down to the last inner product of V with E sub n and square that. And if we now have an orthonormal basis and any arbitrary vector, we can decompose it in terms of a linear combination of those vectors, and we can immediately write down an expression for the norm squared of that vector. And that's true for every little vector v in the vector space. And I think you can almost expect that to be true. You're feeling that that seems reasonable. Let's go ahead and convince ourselves. Let's write the general expression for this vector v. Let's say that it's a1 e1 plus a sub 2 e sub 2 plus a sub n e sub 2. That's our general expression. Now what we need to show is that these scalars, a1, a2, up to a sub n, are actually equal to the inner products that we said they were. Let's now show that a sub L, each of these scalars, is the inner product of the vector v with that particular orthonormal vector e sub L. So now what is that? In this case, if you tell me write a vector v in terms of a linear combination of bases, then you would say, oh, that's a1, e1 plus a2, where my basis vectors are e1 through e sub n. So now you can express any vector in terms of these basis vectors. What we're trying to show is that these scalars are in fact equal to the inner product, where the a sub L scalar is the vector v, inner product of e sub L. So let's now look at that, or in fact, let's form the inner product of the vector v with e1. Bracket v comma e1. But we said in general v can be written as this line up above. We know that it's a linear combination of our basis vectors, so we now have a1 e1 plus a sub 2 e sub 2, etc. up to a sub n e sub. That's v, and we want to inner product that with e1. But what do we know about the first slot? And if we have a linear combination of vectors in the first slot, what can we do with the first slot? We can now do the additivity of the first slot, right? We can now say that, oh, that's a1 e1 with e1 plus a sub 2 e sub 2 with e1, etc. up to a sub n e sub n with e1. And now we can apply homogeneity at the first slot and pull those scalars in. We now have a1 inner product, or times the inner product of e1 with itself, plus a sub 2, scaling the inner product of e sub 2 with e1, and a sub n times the inner product of e sub n with e sub n. And what we want to do now is simply pull in the facts of these vectors that formed an orthonormal list. What do we know if we take the inner product of e sub n with e1? So these are orthonormal, so that's now 0, isn't it? This one, e sub 2, is with E1 is 0, and everything in between those two ordered inner products. This first inner product of E1 with itself is what? By definition, how we define the E1s or E sub L's, that's 1. Or now we can see that we have A1 plus 0 plus 0 or A sub 1. And now we've shown that if we take the vector V, that's some linear combination of these orthonormal vectors, inner product with E1, that is forced to be that scalar A sub 1. And we can repeat that for every one of those scalars. We can inner product V with E sub 2, V with E sub 3, V up to E sub n. So we'll repeat that for all other vectors in the basis. And in so doing, that says the inner product of the vector with these basis vectors E sub L actually returns these. Thus, VE1 is A1, V E sub 2, or the bracket V E sub 2, the inner product of V with E sub 2 gives us A sub 2. And now if we need those scalar weightings on all of these on all of these vectors in our orthonormal basis, we can form the inner product of the vector with each vector in our list. And now that gives us that V is equal to the expression we said in the first part of this theorem. We take the component of our vector, our generic vector V, in the direction of E1. That gives us a scalar, and we just use that scalar to weight that particular vector. Now that we have V written this way, the second half of the theorem is really just utilizing that previous proposition. It tells us about the norm squared of a linear combination of orthonormal vectors. So the second of this theorem, theorem 30, follows. From proposition 625, which says that the norm squared of that vector V is actually equal to A1's magnitude squared plus A2's magnitude squared, where those A's are indeed equal to these inner products above formula or expression or decomposition of V in terms of those vectors E1 through E sub n. That's our orthogonal decomposition. And in fact, you've probably seen that before, maybe not thinking of it in those terms, but you now can start to note the connection with Fourier series. What if we looked at the Fourier series coefficients? C sub n is now 1 over t, where t is the period of our fundamental waveform in our Fourier series, or the fundamental period of our periodic waveform. We integrate over one period. And what we do to find the Fourier series of a generic function is we take that generic function f of 2, we scale it or we weight it by e to the minus j n omega naught t, and we integrate with respect to t. But what is this integral? This integral is actually just, can be thought of as an inner product. It's an inner product of the arbitrary periodic waveform f of t with this. And what is that? That's an orthonormal basis, the conjugate of an orthonormal basis. This is now the orthonormal basis vector, its conjugate, the negative sign, where now we can write the Fourier series of f of t as c1 e to the j omega naught t plus c2 e to the j 2 omega naught t, etc. And we're able to do that because these complex exponentials, these e to the j omega naught t, are in fact orthonormal bases. And if we have little n equal to 1, then we substitute in the conjugate for that, e to the minus j omega naught t. That's now taking two functions and finding a scalar from those functions. That's an inner product. And you've done that probably before. You maybe just didn't think about it in these terms. But now you can think of this decomposition, Theorem 30, that we looked at maybe with these general vectors. If we think of those as being maybe a finite dimensional vector space, we might have been thinking of those as tall, thin vectors, but now we can think of this Fourier series expansion in an infinite dimensional setting, similar to what we just did. Now we're decomposing an arbitrary waveform that's periodic in terms of an orthonormal basis, where the basis vectors are these exponentials, e to the j n omega t. Now, even if these are useful, let's say, okay, orthonormal basis are very useful. Maybe you're saying that how do I find an orthonormal basis given a vector space? But how do we go about finding these orthonormal bases? And like I've done many times in this class, I probably wouldn't ask some of these questions unless I had a nice answer. My nice answer now is another theorem. It's the Gram-Schmidt orthogonalization process. So that's going to allow us to actually create a list of orthonormal basis vectors. So now we're just trying to find, well, what is, we have many different ways of defining an inner product. It just has to satisfy those properties of an inner product. This is not the inner product that we're using up above necessarily. But this what? So this is not an inner product in the bottom line. F of t is just the scalars weighting these vectors, where the vectors are e to the j omega naught t. That's an orthonormal vector. Then we have plus c sub 2 scaling. We're finding these scalars, c1, c2, via this inner product. So if you wanted to, you could write f of t is equal to the inner product of f of t with e to the j omega naught t times e to the j omega naught t, where the inner product is what's up above. That inner product is then c sub n. This c sub 1 is now the inner product of f of t with e to the j omega naught t. Does that help? Now let's figure out how we can find these orthonormal basis vectors. So let's start. Let's say that we now have a list of vectors, v1, v2, up to v sub n. And let's say that that list of vectors is a linearly independent list of vectors in our vector space V. Then there exists an orthonormal list E1, E2, E sub n that has the same span as the previous list of linearly independent vectors v1 through v sub n. So the span of v1, v2, up to v sub n equals the span of v1, v2, up to v sub n. And that's true for all L that belong to those vectors 1 through n. And in this case, let's use sort of an inductive proof. Let's start with the base case, which is, let's say, L equal 1, and assume it's true for an arbitrary length, j, and then we'll show that it's true for j plus 1. Or maybe we just show it by induction for j. Let's then start with the follows. Let v1, v2, up to v sub n be a, meaning it's not b, be a linearly independent list in our underlying vector space. And our base case is L equal 1. In this case, what we do is we go ahead and let E1 be the first vector E1 divided by the norm. Now, I hope that it's clear because the norm of V1 is just a number, isn't it? That's a scaling of the vector V1, meaning the span of E1 is the same as the span of V1. Span is just a linear combination of E1 and a linear combination of V1. Those are, V1 is just a scaled version of E1, so they better have the same span. Maybe. But we also know now that E1 has a norm of 1. And you could look at that and say, oh, let me take the inner product of V1 itself and have V1 over norm of V1 inner product with V1 over the norm of V1, basically dividing this norm squared of V1 by the norm squared of V1 to get norms. So E1 has a norm of 1. We can now continue by induction and assume for a value of j greater than 1, and now we have E1, E2, j minus 1. So we're assuming that this is true up to j minus 1. So continue by induction and say that we're assuming that E1 through E that j has been found. So that the span of V1, V2 up to V sub j minus 1 is equal to the span of V1, V2 up to V j minus 1. So we're assuming that's true. And what we do now is build the j feet. And we'll do that really in 2 steps. First, let's define sort of the numerator. We'll call that W. Take the next vector in our linearly independent list of vectors. Let's call that V sub j. And subtract off the component of V sub j in the direction of each of these orthonormal vectors. Now take away V sub j, V1 in the direction of V1. Subtract off the component of V sub j in the direction of V1. That gives us the amount, and then, or the scaled version of it, we scale V1 with that. And we just do that for all of these vectors, E1 through V sub j minus 1 in our orthonormal list. So we now take the inner product of V sub j with V sub 2 and subtract that scaled version of V sub 2 off of V sub j. And we keep going and take the inner product of V sub j with V sub j minus 1 and use that to scale V j minus 1. This construction process now subtracts off all parts of V sub j that are along V sub l's, where these V sub l's are the vectors in our list, E1, E2 up to j minus 1. And what do we know? We actually know, even after subtracting off all of these parts from V sub j, we still have something left over because we assume that V1, V2, all of those V's were linearly independent. V sub j has to be a little bit different than all the other preceding V's, E1 through V sub j minus 1. Something must be, or something must be left after all of these subtractions, since the V sub i's are linearly independent. And what's left, the remainder, is actually perpendicular to all of the preceding V's. The remainder is perpendicular So all we're doing is we're creating a W sub j. It's a vector that starts with V sub j and takes away the components of all the preceding orthonormal vectors, V1 through V sub j. But what do we know about the length or the norm of Wj? Know anything about it? No. So let's normalize it, and that will give us our D sub j. That's the second step in this process. The second step then is let's let D sub j in fact be equal to what we just built, Wj, divided by its norm. And that has E sub j now is a normal. And E sub j is the same direction. As Wj. And that was perpendicular to the other E sub L's. But now that E sub j has a norm of 1. And if we take 1 and 2 together, step 1 and step 2 together, actually imply that V sub j is now in the span of V1, V2, up to V sub j. Or now the span of V1, V2, up to V sub j is contained in the span of V1, V2, V sub j. We started with V1 through V sub j being linearly independent. The E's are linearly independent. Both lists are linearly independent. And both lengths, or both lists, have the same length. Which in this case is j. Therefore, the subspaces are the same. And the span of V1, V2, up to V sub j is the same as the span of the E's. That's what we wanted. We just had to start with a linearly independent list of vectors, and now we can construct an orthonormal list from that linearly independent list. And that's really quite powerful. And one of the nice things about this particular theorem is that it was a theorem by construction. So this tells us how we can construct these orthonormal lists. Which says, not only know possible. So this wasn't just an existence proof. We not only know it's possible, we know how to construct the orthonormal basis. And once we have this ability, we can really write down some sort of subsequent correlates. A number of useful results now are possible. And I'll just refer you to the text for the details. One is corollary 34, which now is labeled existence of orthonormal basis. By that, every finite dimensional inner product space actually has an orthonormal basis. If somebody gives you now a finite dimensional inner product space, you can build an orthonormal basis from it. You simply have to find n linearly independent vectors, and then you can build an orthonormal basis from that n linearly independent set of vectors. Corollary 35. This one is entitled Orthonormal List extends to an orthonormal basis. For every orthonormal list in our vector space V, can be extended to an orthonormal basis on So now we're assuming, so the question was, this is assuming that we have an inner product, and we're talking orthonormal, that's, I guess, implied by that word. So we're assuming we have an orthonormal list. Then if we're able to normalize these vectors, that's saying that we have an inner product to produce a norm. So by implication, this is an inner product space. So every orthonormal list in a vector space can be extended to an orthonormal basis on V. And another one is now going to be dealing with, another corollary is going to be dealing with maps or operators. So here, this is now corollary 37, which says an upper triangular matrix with respect to an orthonormal basis. So here, now we're saying given a linear operator T on a vector space V if, in fact, that linear operator has an upper triangular representation with respect to some basis. Then that linear operator T, in fact, has an upper triangular representation with respect to an orthonormal basis on V. Where this orthonormal basis we can build using Gram-Schmidt. The orthonormal basis is just the application of the Gram-Schmidt process on the original basis. One more corollary. That was an upper triangular matrix. If we had that on some basis, then we can actually find a linear operator on an orthonormal basis. We just have to perform the Gram-Schmidt procedure on the original basis. Finally, we have corollary 38, which is referred to as Schur's theorem. And that says, given a vector space, V, which is actually a finite dimensional, complex inner product space, and a linear operator T, then we actually know, since it's a complex inner product space, we can always find an upper triangular matrix for that linear operator. So now we can say then T has an upper triangular representation. With respect to some orthogonal basis. Now let's sort of use this to talk about, or these ideas to talk about, orthogonal projection. Now let's say that we're given U, a subset, not a subspace, but a subset, or not necessarily a subspace, a subset of V. Given a subset of our vector space V, we can define orthogonal complement of that subset U. And we will actually label that as U this orthogonal complement now called U perp or U perpendicular can now be quite useful. And this U perp is the set of all vectors in our vector space V that are orthogonal or perpendicular to everything in the subset U. It's the set of all vectors in our vector space V that are orthogonal to all vectors in our subset U. The notation is U perp is the set of vectors V in our vector space capital such that the inner product of V with U is 0 for all vectors U in our subset capital. That's our notation. The U perp is the set of all vectors V in our underlying vector space that are orthogonal or perpendicular or have an inner product of 0 with all the vectors in our subset capital. Here's something that sort of makes you scratch your head. Maybe it's because of the use of the word obvious. But let's say should be obvious. Usually when that gets stated, you know that something's going to be a little bit of a challenge, maybe. Should be obvious that U perp is in fact a subspace even when U is not necessarily a subspace, but a subset. Even when U could be just a subset. We will deal with U being both a subset and a subspace, but right now you're just talking about U being a subset, and we can immediately say that its orthogonal complement is actually a subspace. U is a subset, not necessarily a subspace. And it's okay to be putting on our 2-year-old hat and saying why. So let's now figure out why this is a subspace when we start with the subset. Why is its orthogonal complement, in fact, a subspace? First, this is a little bit wordy, so you may have to go home and read this a few times. But only part, or the only part of V that is not or isn't in our subset U are those vectors that are perpendicular to all vectors in the subset. And if we're dealing with those vectors, we can't get to them, i.e., can't get to the vectors in U, which are actually the vectors B minus U curve. That's U, that's our subset U, through addition or scalar multiplication of vectors in. So if you give me a vector in U curve, and I take another vector in U curve, linearly combine it, those are still orthogonal to everything in the subset. If you use an inner product of that linear combination of vectors in U curve, by definition, they are orthogonal to all the vectors in U. So any linear combination, any linear combination, which is addition or scalar multiplication in U curve, we stay in U curve. And those are two of the properties we need for a subset to actually be a subspace, meaning U curve is now closed. Under arbitrary linear combinations. You give me a vector in U curve and another vector, and I linearly combine those, they're going to stay in U curve because they initially start out as orthogonal to the subset U. Now, what else do we have to have for it to be a subspace? We need it closed under addition, closed under scalar multiplication. That's our arbitrary linear combinations. That's contained in that phrase. But to be a subspace, it has to have the zero vector, doesn't it? But what do we know about the zero vector and its orthogonal properties? It's orthogonal to everything, everything. So you give me a vector in B, in particular a vector little u in our subset, capital U. I can take the inner product of that vector with the zero vector and get the zero vector. That's orthogonal. Zero is perpendicular to everything. So the zero element is in U curve. And so now we've shown that U curve, even though U was not necessarily a subspace but a subset, we've now shown that U curve is in fact a subspace. Let's now look at a theorem based on 47. And this is now the direct sum of a subspace and its orthogonal complement. And here we are going to assume that U is a subspace and not a subset. If U is a subspace, then our entire vector space V is the direct sum combination of U with U. And now we can state a corollary of that, which is corollary 51, and that's talking about the orthogonal complement of the orthogonal complement. Chase my tail. So now I'm taking the orthogonal complement of the orthogonal complement. The orthogonal complement of the orthogonal complement. That's the heading of corollary 50. Here, if U is a subspace, again, we're qualifying U to be a particular, not a subspace. Then, if somebody takes the orthogonal complement, or U perp, and then they take the perp of that, they actually get U the subspace back. U is equal to the orthogonal complement of the orthogonal complement. So I'm playing in a space, and now I take everything orthogonal to it. Then I'm playing in that orthogonal complement space, but now I take everything that's orthogonal to that. I'm back to where I began. That's what I'm saying. Let's look at some examples before our heads start spinning out of control, which they probably aren't, right? So let's now say that our vector space, V, is really big. Let's say R2, just so that our head is still attached. And let's take a subspace. Suppose we now let U be the x-axis. And I think it's clear that that's a subspace of R2. Contains the zero vector, and we can do linear combinations on the x-axis and stay on the x-axis. What is U perp? What's the orthogonal complement of the x-axis? The y-axis. That wasn't very hard, was it? And we know then that we can get back the beginning vector space V is just U direct sum with U perp. So you can represent anything as a unique combination of a component in X and a component in Y. That's basically what we're saying. And if you now take the orthogonal complement of the y-axis, what do you get? You get the x-axis. Now, one more example that sort of plays on these same ideas, but it's a little different. Example 2. Let's say that V is now R2, but now let's let U be 3, 0. Is that a subspace? No, that's just a point on the x line, isn't it? So this is a subset. U is a subset of R2. And what do we know about U perp? If I take all vectors that are orthogonal to 3, 0, what do I get? You get the y-axis, don't you? You get all of the y-axis. And is the y-axis a subspace? Yes, even though we started with a subset. And what's V? Well, V is not U plus U perp, is it? We can't get to every point in V if we only have the ability to deal in the x direction, 1 point, 3. And we also can see then that U don't get back by taking the orthogonal complement of the orthogonal complement. The orthogonal complement of u is y-axis. The orthogonal complement of the y-axis is the x-axis, and that's not the subset of the point 3, 0. And we'll stop at that heady location and pick up on Monday somewhere else in Chapter 6. But maybe it'll be in a projected location.